Hello students, I am Sachitrakar. Welcome to Cars Physics. This is my lecture 19 on electrostatics and we are continuing electric charge and electric field. In previous lectures, we have discussed about electric dipole and electric dipole moment. Also, we have discussed electric field intensity due to a dipole, on axial line of dipole, on equatorial line of dipole, and at any position of a dipole. Okay. In this lecture, we will discuss torque on electric dipole in an uniform electric field. Okay. We will discuss in brief. Okay. Then we will approach some fundamental as well as some application numericals on the basis of electric dipole in uniform electric field. Okay. Then uniform electric field, torque on electric dipole in uniform electric field. Again, I would like to advise the students who have not gone through previous lectures, please go through the lectures, and I have discussed all the concepts in previous lectures. About electric field, we have already discussed on electric field lines. Okay. Electric field lines are directed from positive charge to negative charge. Electric lines of force or electric field lines start from the surface of positive charge and end on the surface of negatively charged body. Okay. Again, electric field is uniform if electric field lines are parallel and equidistant. Okay. We have to find torque on electric dipole placed in an uniform electric field. Let's first represent uniform electric field. Okay. This is representation of uniform electric field. These are electric field lines, and as we have discussed, electric field is uniform if the electric field lines are parallel and equidistant. Okay. Again, the direction of electric field lines are from positive to negative. This represents an uniform electric field and strength or electric field intensity is E. Okay. Electric field vector E. Let's place an electric dipole in the uniform electric field. Okay. This is the electric dipole. Okay. An electric dipole contains two equal and opposite charges. Let this charge is minus q, this charge is plus q. Okay. Two equal and opposite charges separated by a distance, let 2L. Okay. This is the electric dipole. The equal opposite charges are minus q and plus q. Separation between these two equal and opposite charges is 2L. Okay. Again, we know electric dipole moment is product of magnitude of one of the charge and distance between two equal and opposite charges and direction of dipole moment. If dipole moment is a vector quantity, then this unit vector shows direction of dipole moment, and direction of dipole moment is from minus q to plus q, as we have discussed in previous lectures. Okay. Then this is direction of dipole moment, this is direction of P. Okay. This is direction of electric field and this is direction of dipole moment. Then this is angle theta. Okay. This is minus q, this is plus q, let this angle is theta. Okay, means electric dipole moment, this is electric dipole moment P directed from minus q to plus q, makes an angle theta with the direction of uniform electric field. Okay, let this point is A, this point is B, draw a perpendicular, let this point is C. Okay, when an electric dipole is placed in the uniform electric field, what happens? Okay, this is positive charge. This positive charge is attracted towards negative, means positive charge is repelled along the direction of electric field. And as we know, force experienced by a charge in the uniform electric field is F is equal to QE. Then force on this positive charge is QE, and this force is parallel to the direction of electric field. Okay, then this negative charge, we have taken this point is A, then this negative charge is attracted towards positive, means negative charge experiences a force which is opposite to the direction of electric field. Again, since charge is Q, electric field is E, then force on minus Q is also QE. Okay, so force on plus Q means positive charge is QE, force on minus Q is also QE. Okay, so these two forces I am representing here. This is plus Q, force on this charge is QE, this is minus Q, force on this charge is also QE. Okay, see, when an electric dipole placed in the uniform electric field, the two equal and opposite charges experience two equal and opposite forces. Force on plus Q is QE, force on minus Q is QE, and they are opposite in direction. Okay, and we know when two equal and opposite forces act on a body, means if magnitude of the forces same QE and directions are opposite, then resultant force is 0. Thus it is clear that when a dipole is placed in an uniform electric field, then the resultant force on the dipole is always 0. Here we have taken the angle is theta. We may take any angle, any value of theta. Theta may be 0 degree, 180 degree, 90 degree, 45 degree, 60 degree, whatever may be the angle. So I am writing here, when an electric dipole is placed in an uniform electric field, then resultant in an uniform electric field at any position, means at any angle, theta is arbitrary, theta is any value. Okay, electric field at any position, then resultant force on it is always 0. This is the concept when an electric dipole is placed in an uniform electric field. In an uniform electric field, this is important. Then resultant force it and it is always 0. Okay. So in this case, resultant force is 0. Okay. So if resultant force is 0, then we may say the dipole is in linear or translational equilibrium. If resultant force is 0, then the dipole is at translational equilibrium, means the dipole experiences 0 resultant force. Okay. Then about this diagram, this point is A, this point is B. We have drawn a perpendicular. This angle is 90 degree. This is the diagram. This point is C. Okay. Then here, these are two equal and opposite forces separated by a perpendicular distance. Perpendicular distance between the forces is BC. These two forces are equal in magnitude and opposite in direction, then perpendicular distance between them is BC. Again, the fundamental concept, if two equal and opposite forces act on a body separated by a distance, then it constitutes a couple. I am showing you. Suppose this is a body. Okay. Suppose along this direction I am pulling the body with a force F, and in opposite direction I am pulling the body with same force F. Okay. So these two forces are equal in magnitude, opposite in direction. So resultant force on this body is 0. Okay. But here resultant torque is also 0. Why? Because these two forces have same line of action. Simply, I am holding a body. I am pulling the body towards left, towards my left, and pulling the body towards right. Okay. So these two forces are equal in magnitude and opposite in direction, whatever force I do apply. But two forces are same. Okay. Believe me, I am applying whole of my forces. Okay. This force is equal to this force is magnitude, but direction is opposite. Okay. Then resultant force is 0 and resultant torque is not 0, because the body will not rotate at all, because there is same line of action between these two equal and opposite forces. So torque is 0. Okay. The same example, if I take a body, again I do apply to equal and opposite forces. These two forces are pulling forces and these two forces are pushing forces. Again, these two forces have same line of action. Okay. If I hold the body like this and I will push the bodies from both sides, whatever great may be the pushing force, I am pushing with whole of my energy. Okay. I am pushing the body towards left, I am pushing the body towards right, but still the body is at in linear equilibrium, means resultant force is 0, as well as resultant torque is also 0, because here also the two forces have same line of action. Okay. So if line of action of two equal and opposite forces is same and two forces are equal in magnitude and opposite in direction, then the resultant force is 0. I am writing it resultant torque is 0 and also resultant force is 0. Here also resultant torque is 0 and resultant force is 0. But this is the different case. Here these two forces are equal in magnitude QE and QE, but opposite in direction. In this case, as we have discussed, resultant force is 0. but resultant torque is not 0. Okay, I am erasing this because if two equal and opposite forces act on a body separated by a distance, this is the perpendicular distance and this is the distance. AB is distance but BC is perpendicular distance. If two equal and opposite forces act on a body separated by a distance, then it constitutes couple. Okay, see, this is a body. Along this direction let force is F. Along this direction let force is F. Distance between these two forces let X. Here these two forces have no same line of action. This is the line of action of this force. This is the line of action of this force. Okay. So these two forces have different line of action. Okay, and there is a perpendicular distance between these two forces. This perpendicular distance is X. This is X. So if I hold the body like this and apply the force in upward direction, then this force will rotate the body in clockwise order. The seat, just apply the force, it will rotate the body in clockwise order. Again, holding the body, applying the force in downward direction, again this force will rotate the body in also clockwise direction. So these are two equal and opposite forces separated by a distance. If two equal and opposite forces act on a body separated by a distance, they have no same line of action, then these two equal and opposite forces separated by distance constitute a couple. And couple produces torque. Torque due to couple is defined as the product of magnitude of one of the force and perpendicular distance between the forces. Here, this is the perpendicular distance. This angle is theta. This angle is theta. So this angle is theta. Then about this perpendicular distance, from ABC, right angle triangle, BC is perpendicular, AB is a hypotenuse and AC is base. Okay, then sin theta is equal to perpendicular BC divided by hypotenuse means AB. Then this is equals to, since AB, see in this diagram AB is 2L. Okay, then this is equals to BC by 2L. Then perpendicular distance BC is equal to 2L sin theta. Here, this is perpendicular distance, or you may see this force. This is perpendicular distance. This force is towards right. Now I am standing like this, facing towards the whiteboard. This is my right. If you apply the force, then this force will turn the body in clockwise direction. I am applying the force, pulling the body or pulling the dipole towards right. It will rotate the dipole in clockwise order. Also, this is also pulling in towards left. This will pull the dipole in clockwise order. Okay, then torque will be in clockwise order. Okay, then torque due to couple. Torque due to couple is force magnitude of one of the force QE and distance between 2L sin theta. Okay, then torque is equal to, in this case, Q into 2L, Q into 2L into E into sin theta. Okay, then magnitude of torque Q into 2L is a dipole moment into E. Q into 2L is a dipole moment into E into sin theta. This is magnitude of torque. Okay, then direction of torque. See, rotation of the body, rotation of the dipole due to the couple or due to these two equal or opposite forces is in clockwise order. Okay, torque is clockwise, but if you want to know the specific direction of torque, we may take P is sin theta. Theta is angle between dipole moment from minus q to plus q, and electric field vector is along this direction. Okay, so theta, this is direction of electric field. I have represented here the same direction, electric field. So here theta is angle between P and E. So I may write in vector form, torque is equal to P vector cross E vector. Of course, you may write torque is equal to E vector cross P vector. If theta is the angle between dipole moment P and electric field intensity E, P is sin theta, theta is angle between P and E, then torque may be P cross E or torque may be E cross P. Then what is right? We have to see the practical situation. See, this is dipole moment P along this direction from A to B. Okay, and this is the direction of electric field from A to C. Direction is along AC. Okay, this is direction of electric field. This angle is theta. Okay, then as we have observed rotation in clockwise order, if P cross E, this is E. Okay, if you take P cross E according to right hand thumb rule, P cross E shows clockwise, but E cross P shows anti-clockwise. So in this case, torque is in clockwise order. So this relation is not valid. This relation is valid. Okay, if rotation is clockwise, then direction of torque is inwards according to right hand thumb rule. If rotation is anti-clockwise, then direction is outward. Okay, so for direction you may write here inward, you may represent cross. If direction is anti-clockwise, rotation is anti-clockwise, then you may take dot for E cross P. But here rotation is clockwise, so this relation is right. Torque is cross product of dipole moment vector and electric field intensity. Okay, this is torque of an electric dipole in uniform electric field. Okay, so under what condition magnitude of torque will be maximum, and under what condition magnitude of torque will be minimum? We will discuss, we will represent all these. Okay, okay, I am writing the summarization form here. This is about torque, P is sin theta. Okay, so torque, magnitude of torque is P E sin theta. Okay, where P is a dipole moment, Q into 2L, and in vector form torque is equal to P cross E. Okay, theta is angle between P vector and E vector, dipole moment and electric field. Okay, now let's represent again the electric field to have idea about maximum, minimum and zero torque. Let's represent electric field. This is uniform electric field. Let electric field is E. Suppose a dipole is placed parallel to the direction of electric field. This is the dipole. This charge is minus Q, this charge is plus Q, and this is direction of dipole moment from minus Q to plus Q. Here dipole moment is parallel to the direction of electric field. So here angle between electric field and dipole moment is 0 degree. Okay, see, this is minus Q, this is plus Q. This negative charge will be attracted towards positive, means negative charge will be attracted opposite, in the direction opposite to the direction of electric field. This force is QE. Again, this charge is positive. This will be experience a force. This will experience a force along the direction of electric field. This force is QE. See, here theta is 0 degree. Dipole is parallel to the direction of electric field. Again, the dipole experiences two equal and opposite forces. So here, resultant force is 0 and resultant torque theta is 0 degree and magnitude of torque is Pe sin theta. Theta is angle between dipole moment and electric field vector. Then this is Pe sin theta sin 0. Then here resultant torque is 0. Okay. If a dipole is anti-parallel to the direction of electric field, this is case 1, this is case 2. Okay. Again, let's represent an uniform electric field. Electric field lines are parallel and equidistant. Okay. Now, let's place an electric dipole in the uniform electric field. This is the dipole. Now, this is minus Q and this is plus Q. Then direction of dipole moment is from minus Q to plus Q. This is dipole moment P. In this case, dipole moment and electric field vector are in opposite direction. Okay. So since this is minus Q, electric field is from positive to negative. This is negative. This negative charge will experience a force opposite to the direction of electric field. This force is QE. Again, this is positive. This will experience a repelling force, means along the direction of electric field. Again, this force is QE. In this case also, this QE and this QE are in opposite direction. So, I may show the forces like this. I am pushing from both sides. Since these two forces are equal in magnitude and opposite in direction, so again, resultant force is 0. And here, angle between dipole moment and electric field both are oppositely directed. So here, theta is 180 degree and resultant torque is Pe sin 180 degree is equal to 0. So, if a dipole is placed parallel to the direction of electric field, resultant force is 0, resultant torque is 0. Again, if the dipole is placed anti-parallel to the direction of electric field, resultant force is 0, resultant torque is also 0. Okay. Then the third example. Okay. Number 3. So you may write here, this force is minimum, this torque is minimum 0, again force is minimum and also torque is minimum. Okay. So in both the cases, if dipole is either parallel or anti-parallel to the direction of electric field, torque is minimum. Case 3. This is the direction of electric field. Let's consider this is an uniform electric field E. Okay. And a dipole is placed like this. Say, this is a dipole. This is minus Q. This is plus Q. And this is direction of dipole moment P from minus Q to plus Q. And this is perpendicular to the direction of electric field. So here, theta is 90 degree. Okay. But we have to show the force on it. Okay. Here theta is 90 degree. In this case, this negative charge, electric field is directed from positive to negative. This negative charge means this minus Q this minus q will be attracted towards positive with a force QE. This plus q means minus q will experience a force opposite to the direction of electric field. This plus q will experience a force parallel to the direction of electric field. Both are QE and QE. Again, in this case, theta is 90 degree. Again, this dipole experiences two equal and opposite forces QE and QE. So also resultant force is 0. But resultant torque is P E sin 90. So resulting torque is P, which is maximum. So if a dipole is placed either parallel or anti-parallel to the direction of electric field, then resultant force is 0, resultant torque is 0. But if a dipole is placed perpendicular to the direction of electric field, resultant force is 0, but resultant torque is maximum, means PE. In these cases, if the dipole is parallel or anti-parallel, resultant torque is minimum. If dipole is perpendicular to the direction of electric field, then resultant torque is maximum. Okay. So I will discuss about potential energy, that is work done on potential energy of a dipole in the uniform electric field in lecture 20. Okay. In that lecture, I will discuss in brief about stable equilibrium and unstable equilibrium. Okay. But here I will give you idea about stable and unstable equilibrium. Okay. Can I erase all these things? Take first screenshot or note it first, copy it first. Okay. Take it first. Okay. Can I erase now? See. Suppose I am again showing the same case. This is direction of electric field. I am representing an uniform electric field. Electric field is E. Direction of electric field is along positive x-axis. Okay. Suppose a dipole is placed like this. This is minus q. This is plus q. And this is distance between the dipole. And this is center of the dipole O. Okay. So total length of dipole is 2L. Now, dipole is parallel to the direction of electric field. Dipole moment is directed from minus q to plus q. So, here theta is 0 degree. Okay. As we have discussed, if a dipole is placed parallel to the direction of electric field, then resultant force is 0, resultant torque is 0. Now, we have discussed. Okay. This position, if a dipole is parallel to the direction of electric field, if the dipole is parallel to the electric field, then it is the position of stable equilibrium. See children, we already know from, you know it from your previous studies, if resultant force is 0, then the body is in linear equilibrium. If resultant torque is 0, then the body is at rotational equilibrium. So these two conditions satisfy condition for total equilibrium. So the body is at linear equilibrium as well as in rotational equilibrium. But why do we say if a dipole is placed in uniform electric field parallel to its direction, then it is the state of stable equilibrium? Okay. Suppose this is center of the dipole. I do tilt the dipole a little. I slightly rotated the dipole like this. Okay. At this position, now this is plus q, this is minus q. This plus q will experience a force QE, and this minus q will experience a force again QE. Okay. Now see, these two forces equal and opposite. This is perpendicular distance as we have discussed. Then this force will tend to rotate in clockwise order. This QE, see, this is perpendicular distance, this is QE. It will rotate in clockwise order. This is perpendicular distance, this is QE. This will also rotate in clockwise order. So these two forces will rotate the dipole in clockwise order, and again the dipole will orient itself minus q to plus q. Do you imagine? This QE and this QE will rotate the dipole like this. Okay. Clockwise, and again the dipole will align itself parallel to the direction of electric field. So whatever be the position of dipole, the dipole always tends to orient itself parallel to the direction of electric field. This is concept. The tendency of dipole in an uniform electric field is to orient itself parallel to the direction of electric field. Okay. So if I tilt the dipole through an angle, then it will return back, it will come back to its original position, means parallel to the direction of electric field. So this is the position of stable equilibrium. I am showing you if the dipole is in, see, when the dipole is parallel to the direction of electric field, resultant force 0, resultant torque 0. But if the dipole is tilted a little, it will come back to its original position through a very small angle to its stable equilibrium position, means parallel to the direction of electric field. Okay. If I do represent again, resultant torque is 0. Suppose this is the electric field, uniform electric field. Suppose a dipole is placed like this. This is plus q, this is minus q. Then this is direction of dipole moment from minus q to plus q. Means now the dipole is anti-parallel to the direction of electric field. Okay. Theta is 90 degree of the previous case, so that I erased. Okay. In this case theta is 0 degree. Okay. Then now the dipole is placed anti-parallel to the direction of electric field. So in this case theta is 180 degree. And as we have discussed, this is plus q, this is minus q. So this negative charge will experience a force opposite to the direction of electric field. Force is QE. This positive charge will experience a force parallel to the direction of electric field. This force is also QE. See, again in this case, as we have discussed, resultant force is 0 and resultant torque is 0. So if a dipole is placed anti-parallel to the direction of electric field, it again satisfied both the conditions. Condition for linear equilibrium, resultant force is 0, and condition of rotational equilibrium, resultant torque is also 0, as that of when theta is 0 degree. But this is not stable equilibrium. Okay. When theta is 0 degree means when the dipole is parallel to the direction of electric field, it is the state of stable equilibrium. Okay. If the dipole is anti-parallel to dipole if the dipole is anti-parallel to the direction of electric field, then it is the state of unstable equilibrium. Why? What I have already told you, I will discuss the complete concept about stable and unstable equilibrium in next lecture after discussing potential energy of dipole. That will give you complete concept about stable and unstable equilibrium. But here, if the dipole, this is the center of the dipole, this is A, this is B, this is center of the dipole. Suppose the dipole is tilted a little like this. Suppose now this dipole is tilted a little through a small angle. So this minus q comes to this position, this plus q comes to this position through a small angle theta c. This minus q will experience a force along this direction QE. This plus q will experience a force along this direction QE. So again it will rotate in anti-clockwise order. See, it will rotate in anti-clockwise order, okay, like this, and finally minus q will come to this position. It was previously plus q. Okay, we have rotated like this. So it will experience a torque. This is the original position of the dipole. This is the original position of the dipole, means here theta is 180 degree. Suppose this angle is alpha. Okay. So initially theta is 180 degree anti-parallel to the electric field. If I rotate the dipole through a small angle alpha like this, this is the initial position, I do rotate the dipole to this position, then minus QE will experience a force opposite to the direction of electric field, plus Q will experience a force parallel to the direction of electric field. So this force will rotate the dipole in anti-clockwise order. This force will rotate the dipole in anti-clockwise order. Okay. So this position is unstable equilibrium, because again the dipole has to come back to this state, means minus q and plus q like this. But here it will again come back to this position, because here if angle is through a small angle, let here also alpha, okay, rotated through a small angle alpha, then due to clockwise torque it will again return back to its original position like this. But here if it is rotated through a small angle alpha, it will be rotated like this in anti-clockwise order. Okay, so this is the state of unstable equilibrium. Again it will be clarified more clearly on the basis of potential energy. Okay, this is about torque of an electric dipole in an uniform electric field. Okay, I'm erasing this, then we'll have some fundamental numericals on the basis of torque only. The first question is purely on board base, and on board base question you will get only formula based question. Just put the formula. The fundamental formula is magnitude of torque is P E sin theta, or torque is P is Q into distance between two equal opposite charges into E into sin theta. Okay. On the basis of this formula, you will get questions or numericals on board base or fundamental base. Okay. Then first question on fundamental base, two charges plus 2 microcoulomb and minus 2 microcoulomb constitute a dipole separated by a distance of 0.01 meter placed in an uniform electric field of 3 into 10 to the power 3 Newton per coulomb inclined at an angle 45 degree. Okay, find torque experienced by the dipole. Very easy question. See, first we will find theta is given 45 degree. Magnitude of electric field is 3 into 10 to the power 3 Newton per coulomb. Okay, then charge, two equal and opposite charges, 2 microcoulomb minus 2 microcoulomb separated by distance. Then dipole moment is Q into 2L. Charge is 2 microcoulomb, 2 into 10 to the power minus 6. Distance means 2L is 0.01. So unit is coulomb meter. Okay, then magnitude of dipole moment is 2 into 10 to the power minus 6. 0.01 means I may write it directly, 2 into 10 to the power minus 8 coulomb meter. Okay, then torque is P E sin theta. P is 2 into 10 to the power minus 8, electric field intensity 3 into 10 to the power 3, then cos 45 degree. Okay, now solve it to get your answer. It is easier. 6 into 10 to the power minus 5, cos 45 is 1 by root 2, then it will come 3 root 2 into 10 to the power minus 5 Newton meter. Okay, this angle is 45. This angle may be given 30 degree, 60 degree, or it may be asked to calculate maximum torque. If torque is maximum, then you may take 90 degree. Okay, so these are very fundamental based questions. Okay, so these are direct level questions. Torque is equal to Q into 2L into E sin theta or P E sin theta. Okay, if three variables, suppose torque is P E sin theta, theta, P, E and tau. 1, 2, 3, 4. From 4 variables, if 3 are given, then you can calculate the other one. Okay, so from this torque 1, charge 2, length 3, electric field 4 and theta is 5. Out of 5 variables, if 4 variables are given, then we can calculate the unknown variable. So no need to do more questions. So some application based questions and easier questions which may help you for your previous competitive exams. Okay, not previous, sorry. Oh, these are some of questions are from previous competitive exams and it will help you for your future competitive exams. Okay, a system of charges, this is the question. A system of charges minus 2q plus q and plus q are at the vertices of an equilateral triangle of side A. calculate dipole moment as shown in figure. Calculate dipole moment of the system. Okay, if magnitude of electric field is 10 to the power 4 or E, we have already taken variables. I am not taking a numerical data. If magnitude, if the system placed in an uniform electric field E, calculate torque experienced by the system. Okay, diagram is given. This is an equilateral triangle. Each side is A. Suppose here the charge is minus 2q, here the charge is plus q, here the charge is plus q, and the whole system is placed in an uniform electric field E. Okay, a system of charges minus 2q. Okay, system of charges minus 2q, this is minus 2q, this is plus q, and this is plus q, are placed at the vertices of an equilateral triangle of side A, and the system is placed in an uniform electric field E as shown in figure. Then we have to find dipole moment of the system. First, see, this charge is minus 2q. As we know, charge is quantized. Okay, so this minus 2q may be considered as minus q and minus q. So between minus q and plus q, this is a dipole moment. Let this dipole moment is P, and magnitude of P is q into A. This is distance between minus q and plus q. This is minus q, this is plus q. Again, this is the direction of dipole moment P. This is also of same magnitude, q into A. Since this is an equilateral triangle, this angle is theta is 60 degree. Okay, then resulting dipole moment, if I take P dash, then magnitude of P dash I am showing here also. This is P, this is P. Okay, angle between these two dipole moments is theta or 60 degree. Complete the parallelogram. Then this is the diagonal which represents a resultant. If I write PR, resultant dipole moment P, then as per law of vector addition, magnitude of resultant dipole moment is square root of P square plus P square plus 2P into cos 60. Okay, then resultant dipole moment, magnitude of resultant dipole moment is 2P square plus 2P square cos 60. Cos 60 is 1 by 2. Okay, 2 get cancelled, then this comes square root of 3P square. Then magnitude of resultant dipole moment is root 3P. Okay, then we have to find torque. See, again I am representing here, this is direction of resultant dipole moment. This is PR, not P dash, this is PR, resultant dipole moment, and this is direction of electric field. This is direction of electric field. Okay, okay, this is minus q. Okay, this is direction of electric field. So magnitude of these two dipole moments are P and P. Okay, this is resultant PR. If magnitude of two vectors is same, then the resultant must bisect angle between the vectors. So this is direction of resultant shown by alpha, means resultant dipole moment makes an angle alpha, then alpha will be 30 degree. So here angle is alpha, alpha is 30 degree, and torque due to dipole is resultant dipole moment PR into V into sine alpha. Then resultant dipole moment is root 3p into V into sine 30 degree. In place of P, you can write Q into A into V. Sine 30 is 1 by 2. And solving it, our final answer I am writing here. Final answer is root 3 by 2 Q A E. Okay. This is your answer. Okay. Here there is charge minus 2q. We divided minus 2q minus q minus q. Then are the two other vertices charges are, this is plus q, sorry, plus q and plus q. Between minus q and plus q, this is a dipole moment P. This is minus q plus q, dipole moment is P. Between these two dipole moments, angle is 60 degree. Since angle is equilateral triangle, I have brought the total vector diagram to this position. P. Angle between them is 60 degree. Then this is resultant. This is formula for resultant. We get root 3p, and P is equal to Q into A. And this is also direction of electric field along positive x-axis. So this angle alpha is 30 degree. Then torque is P E sine theta. In place of P, we have taken resultant dipole moment into V. In place of theta, we have taken alpha. Alpha is 30 degree. Okay. Then another conceptual question. These questions are very important for your application level, for future competitive like NEET and JEE, etc. Okay. See, I am not writing the question. I am showing you the concept. Let this is x-axis. This is y-axis. Okay. Let a dipole is placed parallel to y-axis. Okay. This is minus q. This is plus q. Okay. Another dipole is placed like this. This is minus q and this is plus q. Let angle, this angle is 120 degree. Okay. Along x-axis there is existing electric field. Okay. These are two dipoles, minus q plus q, minus q plus q. This angle is given 120 degree. Direction of electric field is along x-axis. We have to find torque experienced by the dipole. Okay, I am giving you option A. If dipole moment is P, if dipole moment of each dipole is P, in the given figure, if dipole moment of each dipole is P, then resultant torque is A bit 2p B bit root 3 by 2 P C bit P by 2 D bit 1/3 of P. Quick. So two dipoles are aligned as shown in figure and the electric field exists along x-axis, then the resultant torque due to the system of dipoles given as A, B, C, D. 1, 2, 3, 4. Pause. You may pause your video and think, and you may calculate. Okay. Okay. See it. Okay. See. This is minus Q, this is plus Q. So this is direction of dipole moment. Let this dipole moment is P. Minus Q plus Q. So this is also minus Q and plus Q. So each dipole moment is P. This is minus Q, this is plus Q. Again dipole moment is P. C. This is dipole moment P along this direction. This is also dipole moment P along positive y-axis. So angle between them is 120 degree. Then resulting dipole moment. Then this is resulting dipole moment. Let's take it PR. See, angle between two dipole moment is 120 degree. This is resulting dipole moment. Then resulting dipole moment, magnitude of resulting dipole moment is square root of P square plus 2 P cos 120. And this is equals to 2P square plus 2P square cos 120 is minus 1 by 2, and solving it you will get P. So you know it. If magnitude of two vectors is same and angle between them is 120 degree, then the resultant is equals to magnitude of either of them. Again, now we have discussed, if magnitude of two vectors is same, then the resultant must bisect angle between the vectors. Okay. If this is P, then this is their resultant dipole moment PR. Okay. And this angle is 60 degree. Means this total angle is 60 degree. And this angle is also 60 degree. Okay. Then we have to find torque. This is direction of resultant dipole moment. See, this angle is 60. So obviously this angle is 30 degree. So angle between resultant dipole moment and electric field is 30 degree. Now torque is resultant dipole moment into electric field into sine 30. Then resultant dipole moment is P. E sine 30 is 1 by 2. Then option is C. Okay. Very easy question. Next. Another conceptual question, very important. Okay, I am erasing it without taking your permission. Take it. Okay. This question is very good question. Now I am going to the question, one of the application level question. Okay. See, I am writing. An electric dipole contains charges plus Q and minus Q separated by a distance 2L. Obviously we are taking the same symbols. An electric dipole contains charges plus Q and minus Q separated by a distance 2L is released when it is at an angle theta, released at an angle theta with an uniform electric field E. With an uniform electric field E, if the mass of each charge is m. See students, where there is charge, there must be mass. Okay, then find angular acceleration. Then find angular acceleration just after release. Very good question. An electric dipole contains charges plus q and minus q separated by distance 2l is released when it is at an angle theta with an uniform electric field E. Okay. If mass of each charge is m, find angular acceleration just after release. Okay. If a dipole is released, suppose this is the direction of electric field. Okay. A dipole is held at this position. This is minus q, this is plus q, distance is 2l, mass of each charge is m. When it is at an angle theta with electric field, it is released. Okay. And we know when the dipole is inclined at an angle with electric field, then it will experience a torque, and torque experienced by the dipole is P E sin theta. Okay. Then torque is equal to P. P is Q into 2L into E into sin theta. This is equation 1. Q 2L. Okay. Also, torque is I alpha, where I is moment of inertia. See students, if this is a dipole, these are two charges, mass of each charge is m. This is center of the dipole, this distance L, this distance L. So this is axis of the dipole O. So dipole is rotate about the axis, then moment of inertia. Then moment of inertia, as you know, moment of inertia is sum of mr square. Then here, this is equation 1, torque is sum of mr square, this is m, mass of the particles are same. Then from axis, distance is L, Then total moment of inertia is ml square plus ml square, sum of mr square, mass into square of distance. Then moment of inertia is 2ml square. Then again torque is equal to I is 2ml square into alpha, equation 2. Now this is torque, this is also torque. Equating these two, we will get 2ml square alpha. 2ml square alpha from equation 2 must be equals to q into 2l into E into sin theta. Okay. I am writing here 2ml square alpha is equal to q into 2l into E into sin theta from equation 2 and from equation 1. 2 get cancelled, L square get cancelled by L, then alpha is q E sin theta divided by ml. This is your answer. I have not used any numerical data, I have used only variables. So if the data means the values of q, e, theta, mass and length are given, then you can calculate angular acceleration just after release. Okay, this is very good question and for application for your competitive exams. Next question. Do I erase it? Next question. This is also one of another important question. A dipole is released through a small angle from its equilibrium position in an uniform electric field. A dipole is released through a small angle from its equilibrium position in a small angle, you may take theta, small angle theta, from its equilibrium position in an uniform electric field, let E. Okay. A dipole is released through a small angle theta from its equilibrium position in an uniform electric field E. Okay. Find the period of SHM. Okay, let's examine first if the dipole is released through a small angle theta from its equilibrium position, whether it will execute SHM or not. Okay, see, this is representation of a uniform electric field. Okay, and as we know, if a dipole is placed in an uniform electric field, it always orients itself parallel to the direction of electric field. So this is direction of dipole moment. It is released at an angle theta. So this is parallel to the direction of electric field. Suppose this is center of the dipole. It is tilted through a small angle like this. It is rotated through a small angle theta. This is theta, and plus q is brought to this position, minus q is brought to this position. Okay. Then as we know, plus q will experience a force parallel to the direction of electric field, minus q will experience a force anti-parallel to the direction of electric field. So it will again come back to its original position. Okay. It will rotate in clockwise order and come to its original position. If I rotate the dipole up to this position and held here and released, it will come back to its original position, but when it reaches at original position, it acquires inertia of motion and continues its motion. During its motion, restoring torque retards its motion and it will vibrate. But we have to prove the condition of SHM. Okay, we have to prove the condition of SHM. Okay, as we know, torque is equal to P sin theta. With this torque, I have rotated the dipole to this position. But if it is rotated by the applied torque, it will return back due to restoring torque. Then restoring torque obviously negative. You know it from your previous oscillatory motion subject. Okay. If applied torque is P sin theta, then restoring torque is minus P sin theta. Then it is released through a small angle theta. I do rotated through a small angle and released. If angle is very small, then I may write torque is equal to minus P in place of sin theta, I can write theta. So torque is equal to PE into minus theta. So dipole moment is constant, electric field is uniform, so torque is proportional to negative of angular displacement. Condition for linear SHM. Condition for linear SHM, force proportional to minus x x is linear displacement. Condition for angular SHM, torque proportional to negative of angular displacement. For linear motion force, for angular motion torque, linear displacement x, angular displacement theta. So this satisfies condition of angular SHM. So the dipole is oscillating. The dipole will oscillate in the uniform electric field, and we have to find period of oscillation. Now easier. Okay, we have got, this is formula for torque. This is formula for torque. Then also you know torque is equal to I alpha. If you take this is equation 1, then this is equation 2. Okay. Then now equating equations 1 and 2. Okay. I alpha is equal to P into theta. I alpha is equal to P into theta. Also you know, in linear SHM, linear acceleration is minus omega square y. For angular SHM, angular acceleration is minus omega square theta. This is from oscillatory motion. This is for linear motion. This is for rotational or angular motion. Linear acceleration is minus omega square x or y, and angular acceleration is minus omega square theta. Then I, in place of alpha, I can write minus omega square theta. This is minus P cos theta, P sin theta is theta, minus P theta. So minus theta get cancelled, and omega square is equal to P by I. This implies angular velocity is square root of Pe by I. And as we know, time period of vibration is 2 pi by omega, means time period of rotation is equal to time period of vibration. You know it from oscillatory motion. Then time period is 2 pi divided by omega. Solving it, you will get 2 pi square root of I by P. This is also for objective based question, very important for your future competitive exams. Okay, this is the end of the lecture 19, torque on electric dipole in uniform electric field. Again I have committed in lecture 20, I will discuss about stable and unstable equilibrium, complete conceptual form after discussing work done and potential energy of dipole. Okay, then we will have some numericals on the basis of potential energy and work done in electric field. Thank you students. Thank you for your sincere support. Thanks.